So our next speaker is Sonia Chernova. She is an associate professor at Georgia Tech. She directs the Robot Autonomy and Interactive Learning Lab. They work on developing robots that are able to effectively operate in human environments. Let's hear from her.
Thank you, and thank you for the invitation to be here. Something else is talking over here, but we'll figure it out. Okay, so I love the last few talks. I'm going to try to complement them and highlight similarities that I see as we go along. What I want to talk about is semantics and language for planning, but also like using those concepts not only to improve autonomy, but also improve the way these robots operate around people. I'm going to start with a little bit of history, my own personal history, actually. I got into robotics and I got into it through competitions, through RoboCup, through all kinds of autonomy. And the first like significant area I worked in was learning from demonstration. So I spent many years on getting robots to learn new skills. And we were successful. They learned really cool stuff. But over time, it became less satisfying. And when I found myself doing, I do realize this is a planning workshop, don't worry. But I did realize that we were teaching robots the same skills over and over. And increasingly, I turned to semantics. Semantics, what does that mean? So I'm going to spend there have been so many papers on table setting, on teaching robots how to set the table, or how to hand over something sharp, handle first. Lots of papers on that. And if you look at the literature on human cognition, what it says is that semantic memory that we have in our brains is a type of memory that stores general, often symbolic or abstracted knowledge about the world, and that when we use that knowledge, so efficient retrieval and manipulation of that knowledge enables people to use language more productively, to reason and to plan and solve problems more creatively and more effectively. And so a lot of my work in the last few years has focused on what if I replace that human with that robot? What does that look like for us to be able to use semantic knowledge to achieve those same objectives that we, as amazing machine learning systems, have? So I'm going to do a little interactive test with you guys. You guys are going to be my user studies participants for a second. Let's take this kitchen. I've never seen it before. I mean, I just pulled it off the internet. All right, kitchen. Here's a test. Everyone think about, where are the forks? I need you to find me a clean fork. To make this a little easier, we're going to make a multiple choice question. A, B, C, D, E, F. I'm going to go back so you can see what's under those labels. Everybody decide what letter, where you would look to find a fork. All right, who's looking at E? Raise your hand. Okay, Sandy, check. You're paying attention, right? Most likely not in E. All right, who's looking in F? Who's looking in C? Who's looking in A? Anybody? Okay, so we have about 2/3 in C, the rest in F, and I'm guessing pretty much no one else is in any other letters. If you are, that's fine, but you've been outvoted. The reality is that we have, none of us have ever seen this kitchen before. But we agree on where the forks are because it just makes sense. We know the semantics of households. We know what's convenient. We slightly disagree on which top drawer, but how many people voted on D? Not many, right? The semantics of D don't make sense for us for that object. And we all knew that. And so that is a simple example of the point that I want to make is, what should robots learn? And to me, if we all know that answer, where those forks are, that we've had a 50-50 guess, right? That's not something we need to learn anymore. This is semantic or common sense knowledge, however you want to call it, that we can just look up. And that changes how we think about robots, because it shifts us from having to learn to being able to plan. And that's where this workshop comes in, right? Because now we can plan instead of having to learn everything from scratch or from demonstrations. And that can be at the motion level, where I know I need to hand this sharp thing to you, and I can do that handle first. Or it can be at the task level, where I'm trying to find a fork so I can set the table, but I already know from semantic knowledge what table setting looks like for humans, right? And so to me, that's like part one. That got me really excited about semantics. Let's not learn everything from scratch. Now let's talk about semantic data in more detail. There's been a lot of talks, right? We've seen a lot of examples. You've all seen papers. But there's a lot of different ways to represent semantic data. So I just want to make a point in case someone in the audience is sort of like not really yet sold on this idea. One is language, right? We could say a ballpoint pen is made up of these parts, or is located at some location like the desk. Lots and lots of kind of graph representations, ontologies that have been used, WordNet type stuff, all that. But in robotics, we also love the types of examples Nick just showed, right? Or Dan Fay showed earlier, where we have space. We want to be able to reason, oh, well, I'll navigate the hallway, secure the area, right? What is the area? And so semantic space labels, regions of space. We of course have semantic scene graphs. Computer vision has used semantics extensively. And then you can even drill down and talk about object parts, like the handle of a knife versus the blade of a knife, and the rim of the cup versus the part that contains the liquid. So lots of these. None of these are not my works. I'm just using examples from across the literature. And if we boil all this down, so everyone, we all use that term semantics. It means something different to everyone, depending on what you're doing. But at the highest level, it's all data abstraction. And almost always it leads up to word labels. We don't really know as a field, as a species potentially, to talk about semantics without using language. It's very rare that we don't start to put word labels on it. Even when we do regions and visuals, we almost always are like handle, right? And that's great because we now have a way to communicate that. And all of that's communicating is these abstract concepts of facts, ideas, beliefs, regions, and so on. So in summary for this first part, I'm going to build up this summary as I talk. The summary is, first of all, there's many different ways to represent semantics, right? What are their visual, geometric, textual? They all seem to lead to language for us, which is nice. Because it leads us to other things we can do, such as the power of LLMs. And the other thing I want to get across is that when it's available, let's not ignore it, right? Let's not keep teaching robots where to find forks. Let's try to be just proactively using some of this common sense knowledge in techniques like planning. And of course, I'm not the only one with this idea. Lots of other people are using this type of information for everything, including task and motion plan. And I'll give a quick example of something you can do very, very simple with this type of knowledge. We played, it's kind of almost like hide and seek. It's not quite hide and seek. It's more like I Spy. We actually set up a robot. We spent several projects, this is before LLMs, doing object finding. And in this one project I want to show very briefly, we had a robot in a household setting, and we would say, okay, where can you find a dirty sponge? Where do you find a dry sponge? Where do you find I don't know, a wet cup? And so like really just using various descriptions of objects and seeing how quickly the robot can find something. And for fun, we also had people do it. So we brought people into this environment. We compared robot performance or AI performance against human performance. And we gave everyone three tries to find something. So in the first try, humans were 65% accurate. So this is the same example as what you just did for me with the kitchen and the fork, right? And I'd say, where is your first guess accurate? First guess was 65% accurate. Second guess for humans is 83% accurate, or 83% of the time they've now found the object, and 91% of the time by the third try they've found the object, right? Interestingly, with this is a transformer-based architecture, we were at 88, but by the third try, we're very close to human performance. With no learning, no personalization to this environment, just pure semantics. And so that kind of gives you the power. And I think coupling this with planning-based systems gives you that ability to just, what does that give you? It gives you the ability to adapt to new environments, right? What we now call zero shot a lot of the time is now we have the ability to not hard code everything, to be able to put the robot in a brand new house, brand new kitchen, and have it actually have a reasonable chance of finding stuff without having the most detailed SLAM, the most detailed 3D map, because it's using common sense knowledge, right? So it gives that power to planning, I think, that we should be seeing more of. Okay, so that's one quick example. I want to spend the rest of my time on two examples that actually now have to do more with users. And I want to bring it back to something we've heard throughout ICRA, I think this week. Nick sort of mentioned elements of it as well. And that's that when we talk about autonomous robots, we very rarely talk about no humans in that autonomy. Even when we especially when we send robots to Mars, humans are in the loop. But even with Roombas, they're somewhere in the loop. And so I want to talk about what's the human element sort of in this planning framework. And I wanted to two examples. One is going to be about explainability and explaining plans to users. And the idea is, okay, we have some sort of task plan. The robot has a plan. Great. As we get more and more complicated with these plans, they're going to break. We're going to be more adventurous getting robots out there. Things are going to go wrong. Inevitably, users are going to say, why are you doing this? What are you doing? Robot, what are you doing? And at that point, we want the robot to be able to explain what it's doing. And here, we want to use language, right? Because that's how we communicate. So the question is, to us, was if you have a plan, like a PDDL plan, how do you explain this? Right? And there's been a number of others working in that space as well. And we came up with this idea of sub-goal-based explanations that to us felt like maybe a small incremental like improvement, but like a really core missing piece of the literature at the time. This was 2023. We did this work instead of robots on Overcooked because it allowed us to test with hundreds of users very quickly. But I think that the insights that are here actually do transfer quite nicely. So here's the setup. How many people have played Overcooked? Anyone? Yeah. All right. It's increasingly being used in AI. You guys are so interactive and so good at raising your hand. Good job. So Overcooked is there's time pressure. You're cooking. It's like a restaurant kitchen, right? It's a fun game, and it's been increasingly used in AI because it's actually really hard to be optimal. In fact, I would argue that no one in this room will play that game optimally. It is incredibly hard to optimize this task on these harder levels. But cool, but we have planners, we have AI, right? So we can run AI really fast and we can generate plans. And so we came up with an interesting scenario. Let's say we instead of automating the AI and the robot or the character, we're going to let the human play. Let them keep playing themselves. That's what humans like to do. But we're going to try to help them get better at the game, and we're going to explain what action they should do. And then we're going to evaluate how well our explanations work. The thing we're trying to optimize is these explanations. We're going to see how well they work based on how well people are able to play the game. But the key factor here is not only are we trying to teach, we don't want to assume that our planner is optimal. As many of us know, planning is often suboptimal. And that means that sometimes it makes mistakes, and that means sometimes its recommendations will be wrong. And that does tie back to a lot of work we've done in robotics and robot failure, because failures also happen, and that's another place you really want to explain things. And so one thing we did was we purposefully corrupted plans and sometimes had them say, yeah, do this. And we worked really carefully to make it super plausible that that would be the right action. But coupled with the explanation for why, if people are paying attention to the explanations, then what we wanted to see, can they discern the difference between like a good action and when the system's actually making a mistake? And so there's some really interesting results to me in this paper. So very briefly, the way this is set up is we have a plan as a sequence of actions from some sort of closed set of actions A that goes from some initial goal state to some final goal state, initial state to some goal state, right? And a sub-goal-based explanation is basically consists of two parts, right? You're telling the user what action they should perform. We're framing this as an intelligent decision support, so IDS. So what action they should perform, and then we're also specifying what sub-goal in your overall plan this action will satisfy. Why should you bother doing this action? And this is actually interesting because in many cases, an action can satisfy many sub-goals. And there's some nuance there that I don't have time to get into. And so in order to figure out which particular sub-goal to use, we can actually use linear search on the policy or on the plan in this case to figure that out. And so we developed Overcooked, or we took one of the open source variants of Overcooked, and now we don't have to look at this too closely, but there's just recipes and things that we're telling the user to do. They can go around, do all kinds of actions. We tell them what's where, but we also add this little avatar that says, hey, you should move the bell peppers to the plating station for making the quesadilla, right? And it sort of explains things. And the way we integrated all this into planning is we're using temporal pass downward for planning, and then we're corrupting about 15% of its actions by moving around and making things suboptimal on purpose. And the action cost here is whether you take too long to deliver meals, which is the usual Overcooked metric. And we can do this. There's a nice automated framework. I'm not going to talk about all the details, but we're comparing sub-goal-based explanations against two other baselines. One's just giving the user the action, which some other folks have had good effects with, just like, hey, do this. This is your next thing you should do. This is intelligent decision support, quite common. And then another is called causal link chain, right, which is telling in the context of planning, preconditions, postconditions, and effects, obviously, right? You can sort of track the chain of effects of this action and explain why it fits into the sequence. And some people have done that as well. Now, looking at the results real quick, I'm going to show you three different graphs. The first one is not the most impressive, just kind of sanity check. How often do people avoid the bad actions? Forget all the good actions. If they're following our good actions, that's great, whatever. Maybe they were going to do that anyway. But we told them to go chop the lettuce, even though that was completely irrelevant. How often are they avoiding it? And you want to see 100% here, right? That they're doing a very, very good job at avoiding the bad actions. These are the three conditions. Ours is the one on the left. And we're seeing a reasonable, so there's two different overcooked scenarios, which is the yellow and green. But they're doing a good job, and it's actually better than with the other methods. Fantastic. So they seem to be able to like hone in on when we're giving them a bad advice, even though we've made it subtle. Okay, does this really mean anything? All right, let's keep looking. Now let's look at the overall, again, two variants, left and right, are just two different, one is tacos and the other one's called Asian bistro. It's just two sets of recipes, two different environments. We just didn't want to overfit to one overcooked scenario. But now we're looking at plan cost, like how effective are they doing it? Basically, what's their score on the game, right? And here lower is better because then you're not getting your meals late. And with our condition, we're getting really, really low scores. This is good. But right now we're still advising people. We're telling them what to do. And again, is that enough? Is that the interesting result? Like, are we there yet? Here's the interesting result. I'm going to turn off the explanations. They've had 2 games. They only get 2 games with explanations. And I'm going to play a third, and we turn them off. What happens then? Learning effects, right? Everyone learns to play the game. Everyone gets better. Even when they got no explanations, which is this nice blue one on the left, they got better. Their overall cost is not that bad. But in the grand scheme of things, our method here is a ground truth one and a noisy one, but I'll just talk about this one. Is not only the best, but look what happens in the other cases. The other cases looked good before, and this is when you just say, chop the lettuce, carry this, do this, right? People were good at following instructions. Great. Now that you took away that crutch, turns out they don't actually know how to play the game. Why do I care about them playing the game? I don't. I really don't. What I care about is, what if this was a robot? Did they learn to understand my robot? No. They were just sort of like, oh, it said this. Cool. Okay. It's like the robot said, if your robot said, plug me in. Okay. Did that fix anything? Did you understand how the robot works? No. And so what we found out is, through something like sub-goal-based explanation, even better than link chaining, we can get people to understand the inner workings of this particular task. And it's really interesting to now think about the jump to robotic systems and whether explanations can help us understand robotic systems. So in summary, pulling back the ideas from before, as we develop more complex planning systems, task planning and so on, we need methods. I think it would benefit us to have explanations about how the inner workings work, and something like this could help with that. I didn't really motivate the need for it very much, but I did show that what we can do is, once you have those explanations, people actually learn not only the explanation at its face value, but deeper about the underlying task, the abilities of the robot, if the robot's failing, and so on. All right, in the last few minutes, I'll just show my other example real quick with users. This is relating to the productivity work I talked about earlier in the week. Some of you might have seen the first couple of slides before, which is here we're doing something completely different. The example here says, has a robot driving up to a user and saying, I brought you oatmeal, because you usually have it with coffee. And this is a project where we were trying to do longitudinal proactive assistance, so anticipating user needs ahead of time without being asked, and seeing what objects they need. And we could do that with first with spatial temporal object tracking. So we just tracked how objects move through space and tried to predict what objects would be where. Then we got fancier and started to use a more complex model with activity recognition and other factors. And the reality was like, the more info you use, like recent history, activities, time, all this stuff, the better performance you can get. And this is fine. I'm not going to talk about this, but this is great work published at Coral a couple of years ago that was really fun to do, just about like how well can robots predict what we need. But this led us to this question of, do we want robots to always predict what we do, right? So if I come in the house and I throw my shoes in the middle of the floor, and then I don't know if my dirty socks are in the living room floor, none of us ever do such things, but like, okay, does this mean the robot's going to learn to, oh, let me get these shoes out. Throw them over here, right? Oh, let me sprinkle some dirty laundry for you. We don't want robots to learn certain things, right? But even getting beyond that, there's a lot of preference actually about what we want robots to even do at the task level. And we got into this, especially with older adult users. We started to collect their preferences about what robots want to do. So we actually took a stretch. This is a collage of the various videos we showed them, but like started getting robots to put away dishes and water plants and do all kinds of crazy stuff, drilling their wall to hang up a picture. We have like really easy stuff, kind of crazy stuff in there. And we went to older adults and said, talk to us about these robots. They gave us 178 things they wanted robots and not wanted robots to do. They got really detailed, and they got really detailed in a really interesting way, saying that, I don't want it to be loud while I'm sleeping. If I'm taking a nap, don't put away the dishes. And this is now language, brings us back to semantics. What does that tell you as a person? If it was you and your partner is sleeping and taking a nap, should you get the vacuum out? Should you start, oh, I know, let me drill a new hole in the wall so I can hang up some posters or whatever, right? There's all kinds of interesting things that language carries. And that brings us back to the semantics and language piece. As far as personalization, by the way, our users did not agree on anything. If you run phones cap on it, 0.23, that's incredibly low agreement between what they wanted robots to do. And interestingly, if you tried to learn any one of their preferences with rules, you'd need 76.5 rules on average for every 100 different tasks the robot would do. So constantly asking the user, would you want like this? Would you like this? Would you like this? Would be really, really time consuming and really exhausting for the user. And so the last highlight I want to give is our work on using language, and that language they say, which is don't do this loud thing because I'm sleeping, to carry over into the effects of all the other tasks, right? If you have a planner and lots of tasks or primitive actions that the robot can do, or sub goals, whatever way you want to think about it, we can use language to, in particular LLMs, to characterize, to find characteristics of that task. So if we know where that task is, what objects it involves, what location of the house, we can actually use LLMs to learn, to query an LLM and say, is this loud? Is this potentially dangerous? Am I going to break something? Is this fragile? None of this is encoded in PBDL, right? We don't know that. We don't want to encode that in PBDL. But now we can couple this with LLMs so that when the person says, don't do X because it's loud, you will also not do all the other stuff that's loud. And that's what this is supposed to show, right? Noisy action, this is the one the user said, we also will block off all the other ones. And this works well, and it works better than LLMs by itself. There's a nice architecture we have that's better than off-the-shelf LLMs. All right, my last piece of summary from that is use language, use semantics. We can use it in planning to affect kind of what is executed in a meaningful way. How do we personalize these systems? Okay, I'm at time, and I'd like to thank all my co-authors who contributed to all this, and I'll be around for a few minutes. And thank you again to the organizers for having me come. Thank you.